We continue with the second part of the class. I said before that the first hour has been mostly a refreshment of concepts of the methodology that we follow in the direct stiffness method. Now we are going to spend the second part of the class to make an introduction to finite element modeling. Not to any finite element modeling, but focus to structural analysis. Okay, so what are finite elements and what do we use finite elements for? Now, what is a finite element? And there are different ideas about what a finite element is, depending on who do you ask. Let's go back many, many years to the 3rd century before Christ, and let's put a classical geometrical problem to ourselves. Let's have let's have a circumference, and of the circumference we know the radius or the diameter, and we want to know the ratio between the length of the circumference and the length of the diameter. That is, we want to calculate pi. Okay? And there are several ways of doing it, but Archimedes solved the problem by constructing a series of inscribed regular polygons inside the circumference and computing the length of the perimeter of the polygons. Okay? So he constructed this series and he thought that it would converge to the correct value of pi if done properly. Now, this is not exactly finite elements, but we can do this exercise. And then we do this exercise and we find that if we use 2, 4, 8, 16, 32, 64, 128, and so sides for the regular polygon, we may we can compute an approximation of P which is equal to 2, 2.82, 3.06, and so on and so forth, until for this many-sided polygon we have a value of 3, 1, 4, 1, 5, 1, 3. By the way, this is the exact value of pi, up to 16 places. Now, as an engineer, how many exact places do you need? It depends on the application. Very good answer. Okay? You may do with 3, or you may need a lot more. Okay? So it depends on the application. Now, this is by using the straightforward method. If you want to be a little bit finer, you can do from these two values, and using a extrapolation method, you can already produce this value. And using these two values, you can already produce this value, which is not that bad. Okay? And by using these two values, you can already produce this value, which is not that bad at all. Okay? And so on. So, on one hand, by using this very simple procedure that Archimedes invented of, rather than looking philosophically at the circumference, looking at something that he had more at hand and easily computed, the regular polygons, well, he constructed the series and he constructed, in fact, he produced a method to compute pi with as much precision as needed. Okay? This is one idea. The second idea we have already presented before. We have, on one hand, the physical reality, the physical model, but we need to idealize and discretize it to be able to compute it. Okay? In some instances, few, but in some instances, the mathematical model, which is itself an idealization of the physical reality, it is discrete, but not always. Okay? if rather than being this sort of truss in a roof, we would be concerned with the deck of a bridge or a tunnel inside a mountain or an arch dam or something like that, well, the mathematical model would not be discrete. Okay? So we would need an additional step of discretization to be able to put it into a digital computer. Okay? Now, this is the second idea. Now, coming from one thing and from the other, we can present two interpretations of the finite element method for a master class. This is the presentation for engineers, let's say, and this is the presentation for mathematicians. Now, for engineers, for most of the engineers, the finite element method consists of the breakdown of the structural system into components, elements, pieces, parts, and then reconstruction of the structural system by the assembly process. So this is exactly how we have been presenting it before. Okay? We have the structure like a Meccano, and we sort of play with it mentally, and we break it down, recognize the properties and the behavior of one single element, and then we put it together, and we use words like assembly, okay? Which is a rather engineering word. Now, on the mathematical side, well, a mathematician would never say something like this. A mathematician would say that it is the numerical approximation of a boundary value problem by a Ritz-Galerkin discretization procedure with functions of local support, which is absolutely correct. Okay? So in this, in this master course that you have chosen, you will hear this a number of times, this a number of times as well, and it's for you to make the adequate merging of the both. Okay? I will usually refer to this, but I will sometimes as well refer to this one. So I want you to know here, surely in other subjects they will make more effort, what does this mean? Okay? Now, again, I'm not going to repeat, but the finite element method fits exactly here. Okay? The finite element method is not going to help you to do this, and it's not going to help you on this. Okay? It's of no help. It is of help exactly to do this, to discretize a mathematical model, to create a discrete model, and then it's up to you to get the solution of the model and to make sure that your solution error and your discretization error and your modeling error are inside the allowable bounds. Okay? But the finite element method is not a solution for everything, it's just a tool to cross this gap. Now, if you recall the steps that we have said before, the disconnection and the localization, which are mainly conceptual, gets you to consider the formation of the matrices and the vectors, the arrays, of a generic element. Because once you have that, you continue with the globalization, the merging, the application of boundary conditions, the solution and the recovery, and that's quite standard, and that's quite the same for all the elements. So, because all of these operations, the first two are conceptual, and all these operations are element independent. So let's spend some minutes considering the elements. What do we mean? What do I mean when I say that you have different elements in the library? Okay, and that's what, if you use a commercial or not so commercial finite element code, it will say we have an extensive element library. You can choose from a number of elements. Okay, what does this mean? Why an element is different from another? So we can spend some minutes discussing this. Now, a finite element, a mechanical finite element, has a number of attributes. So let's make a list. For instance, a finite element has a dimensionality. We have 1D finite elements, 2D finite elements, 3D finite elements. We have asymmetric finite elements. Okay? We have, you will also see, we have infinite finite elements, which is a contradiction in itself. Okay? Now, you will see them. Finite elements have nodes. Okay? And nodes serve at least two purposes. First, they define the geometry. Okay? You cannot have a triangular finite element if you don't have three nodes which define the triangle. Okay? It is true that you may have triangles with more than three nodes, but three are necessary. You cannot have a quadrilateral finite element if you don't have four nodes at the corners. You cannot have a tetrahedral finite element if you don't have four nodes at the corners of the tetrahedron, and so on. And usually, the nodes are also the home for the degrees of freedom, as we have seen in the example. Okay? Not only the nodes indicated to you that the bar went from node 1 to node 2, but it's also the degrees of freedom, the translation of the nodes, were the degrees of freedom of the element. Now, apart from having nodes, an element is defined by the number of degrees of freedom it has. Okay? Usually sitting at the nodes, but not always. Necessarily linked to the degrees of freedom, you have the conjugate nodal forces. Because as you will see in this class and in other classes, many of the theory behind finite elements comes from either work theorems or energy theorems. To have work done, you have to have forces making work on displacements. Okay? And for that, you need conjugate nodal forces doing work on the nodal displacements. Okay? On top of that, you have material properties and you have fabrication properties. That's a differentiation. What is a material property? The Young modulus is a material property. What is a fabrication property? The area. Okay? The thickness. Okay? They usually go together. I mean, you have a product of them to define the stiffness of the element. Now, for instance, you see here we have one element in 1D, another element in 1D, another element in 1D. But this has two nodes, this has three, this has four. Okay? These are elements in 2D, and they are triangular. And these are also elements in 2D, but they are quadrilateral, sort of. Okay? These, and these, and these, and these are straight-sided elements. But these, and these, and these, and these, and these, and these, and these are not. Okay? So there are a number of finite elements, and there are a number of things we can do, and certainly there is a library of them we can choose from. Now, mechanical finite elements, as everything else, can be classified. Now, let's attempt a rough classification. Some of them are primitive, some of them are continuum elements, and then we have special macro elements and substructure. Macro elements and substructure are, well, more or less the same thing, as you will see. Now, what do we mean by primitive structural? By primitive structural finite elements, I mean elements which were born before finite elements existed. For instance, the one we have been playing with before. Okay? We have been solving a problem with truss bars, and truss bars and the formulation for truss bars existed many years before finite elements were thought of. Okay? So let's say we are borrowing mechanical behavior, mechanical elements from our This means mechanics of materials. You would have studied mechanics of materials or strength of materials, which is the traditional name. So we are borrowing elements from those classical disciplines, and we are using them as useful finite elements. Okay? And then depending on the application, we can use bars, you see, like the bar we used before. It's a simple element that only works under axial forces. We can use beams. It looks very much the same, but this works under bending. Tubes or pipes, which again look very much the same, but they incorporate torsion. I could have listed shafts. You see, shafts for mechanical engineers. I could say this is a shaft, okay? And it looks very much the same, but it works only under torsion, okay? Now, you can have a spar, which again looks very much the same, but it works for shear. And the 2D version of this, which is a shear panel, okay? You need shear panels in planes, in wing planes, and you need shear panels also in buildings for anti-seismic resistance. Then we have the, let's say, real finite elements. The real finite elements, to these real finite elements, is to what we are going to devote the largest part of the first part of the subject. So we will have triangular or quadrilateral finite elements to do elasticity in 2D. Okay? Or we will have tetrahedral, hexahedral, and prism elements to do elasticity in 3D. Okay? So how do we go from the theory of elasticity to the formulation of these elements? We are going to devote to that the several next classes. Okay? And then we have special elements. Special elements come in fashion and go out of fashion depending on applications. In some times there were, a crack element was in fashion, something like this, with the crack inside. Why do you know fracture mechanics? In fracture mechanics, this point at the tip of the crack is a singular point. So in the neighborhood of the crack tip, you have a very singular strain and stress field. So if you don't do something special, then you are not representing correctly the theory behind. Okay? So that was proposed. Here you have the famous infinite finite element, okay, which is used to study domains which are unbounded. Okay? Domains which don't have a limit. So you think, for instance, you think that you have a 1, 2, 3, 4, 5, 6, 7, 8 node, an element like this. Where was it? An element like this, for instance, and then you do something so that these 3 nodes are mapped into the infinite. You use a clever mathematical transformation to send these 3 nodes to the infinite. And then you have something like this. You see? This is very useful, for instance, when you have wave propagation, because you don't want your wave to propagate, hit the artificial boundary, and rebound. So you just do something to put your boundary in the infinite. So it will take forever to reach. Okay? Then you have other elements like this, the honeycomb panel. This is a sort of a combined shell element. You have a shell element here, you have a shell element here, you have something in the middle which is very rigid but it's not resistant, and then you combine the degrees of freedom of this and this, and you have a special element. Okay? So these are special in the sense that they are for special applications. More interestingly, you have macro elements. What is a macro element? A macro element is that you combine some elements to create a new element. For instance, you can create a quadrilateral element by combining 4 triangular elements. Okay? So you know the stiffness matrices of these 4, you sort of assemble them, you condense out the degrees of freedom of the central node, and there you are, you have a quadrilateral element made of triangular elements. That may be handy sometimes. For instance, here you combine 4 plate elements to have this sort of pipe element, okay? Hollow box element, okay? Now you make up your structure with this element, this macro element, rather than with this, okay? An oversized version of this is substructuring, okay? You have an aircraft, and you build the aircraft by assembly of substructures. You have substructure number 1, which is the fuselage. Number 2 and number 3 are the wings. Number 4 and number 5 are the tail wings, and number 6 is the tail. So you construct finite element models for the tail wings, for the fuselage, and that's our partial models that are substructures, and you condense out all the degrees of freedom here, and then you assemble these as a macro, big macro element, okay? Now, some examples of what do we use this for. Examples of structural models coming from different branches of engineering. This is a mechanical part, okay? Mechanical parts look this strange. Well, certainly they do look strange for a civil engineer, because civil engineers always think in terms of beams and columns and plates, okay? Obviously, mechanical engineers, not necessarily, okay? So there is no beam theory to be applied to a part like this, okay? Or a crankshaft, okay? Or part of an engine. I mean, that's solid, okay? So if we want to analyze these, well, we need finite elements. Now, on the other hand, some of our structural models are not exactly conventional, okay? This is a Gothic cathedral. This is a Gothic cathedral. It's Tarazona Gothic Cathedral. And sometimes you are called to study, to have a look at the structural behavior of a building which is not conventional. I mean, it has not been built with the standards, current standards. Some other times, you have structural models which are very complex in many senses. For instance, we are trying to study here what happens to a dam. This is a gravity dam made of concrete under seismic action, okay? And you see that here we have a number of things that we have to consider. We have a base rock, we have sandstone here, we have unsaturated soil here, and on the other hand we have saturated soil here. Saturated means that water is inside. And here we have water, but the part of the water which is closer to the dam, particularly if the dam is high enough, under motion may be cavitating. Cavitating means that it goes nonlinear, and that is extremely harmful for the dam, because it will sort of cause explosions. Okay? When you have something solid moving rapidly in a fluid, you have to watch out for cavitation. That's a typical problem for submarines, for instance. Okay? So, well, that's a complex problem, not easily studied from what we have been taught previously, in the previous years. Okay? So we need some more powerful weaponry to attack this sort of problem. Now, this is from marine engineering. This is a supertanker. Okay? A supertanker is difficult because this is a typical cross section of a supertanker, and you have all sort of things inside. But basically, a supertanker is a beam, okay? The load is inside the beam. The support is the water. So it's not supported at the ends, it's supported all over. And it's working mainly under bending and torsion. Torsion to be avoided, and the bending to be avoided if possible. Because it's working mainly under bending and torsion, it has this typical cross-section for a torsion beam, okay? With different stringers and frames and girders and so on. It's a typical structural model, okay? Even if it is a tanker. Now, if we go to a plane, then it's even worse. This is the Eurofighter, the F-16, and if we look, well, these are finite elements, and if we look inside the wing, then it is something like this. Okay? So it is complex. So there is no wonder at all that finite elements were invented by a company who wanted to make planes. Okay? There's no, I mean, probably we could have gone building bridges without finite elements for some more time, but no way they could do planes without finite elements. Okay? By the way, planes are not standing still like bridges. Planes fly. Okay? So it's a little bit stupid to think that structural analysis ends with static analysis. Dynamic analysis is as essential as static analysis. And secondly, and I will come back to this idea in some weeks' time when you are a little bit softened, have you seated by the wing of a plane sometimes? Yes. You see the wing. You see the wing doing things like this. That's not a small displacement, is it? Okay. So the wall does not end in statics, and it does not end in linear behavior, and it does not end in small displacements. Okay? And you must rely a lot on aeronautical engineers because you pay 30 euros, you sit there, and you believe that you are going to get safely to the Canary Islands. So you must have a lot of confidence in the finite elements that the Boeing or Airbus company is using, which is good. Now, some general modeling rules. Because we have different elements, and some of them are very sophisticated, use the simplest element that will do the job. So be sure that you know what the job is, and then use the simplest. Okay? Never, never, never use complicated or special elements unless you are absolutely sure of what you are doing, which is a very, 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 very simple rule. Okay? You have this beautiful, this magnificent code with this huge library of elements. Use the simplest until you are sure that you can use something else. Use the coarsest mesh that will capture the dominant behavior and the physical behavior of the physical model, particularly when you are designing. Okay? Engineers spend a lot of time designing things. That means that they are not really sure of how the final model is going to be. Okay? So there is obviously no need of spending a lot of time, a lot of effort, a lot of resources in creating very fine meshes to get very accurate results on something that you are going to change tomorrow to get another model. Okay? So try to grasp, which is not DC, which is the dominant behavior that you want to study, and then make sure that you are doing that right. Okay? 3-word summary. Keep it simple. Okay? Now, where do we need finer meshes? Well, we know that. Generally speaking, we need finer meshes when we expect stress concentrations, okay, and strain concentrations. And we expect stress and strain concentrations near cutouts, at the tip of cracks, when we have entrance corners, like here or here, not here. When we are in the vicinity of concentrated points, like here, concentrated loads, or contact points, like here, okay? Weldings, like here. When we have a sudden, abrupt change of thickness, because here we are going to have, for this element, we are going to have concentration of stresses, and in the other, we are going to have the contrary, okay? And when we have material interfaces, because that's a similar case to this one, okay? Depending on the properties of the two materials. Now, when we create meshes of finite elements, we must try to avoid bad aspect ratios. So this is good, and this is bad. Why? Because when we have a look to the stiffness matrices of the elements, we will see that the stiffness matrices are built of differences of lengths, differences of squares of lengths, and things like this. Now, if the lengths of the elements are similar, these operations are okay. Well, never do finite elements without double precision, never, because it won't work. But if we have big differences in lengths, so like this compared to this, when we make differences of lengths or square the lengths or whatever, we're going to have run-off error. And it's going to affect the solution, okay? So it will easily go unnoticed, but we are going to have what we have shown in previous slides. We are going to have solution error, and it will mostly go undetected, okay? On the other hand, we are not going to do the mesh by hand. So we are going to have maybe a 3D complex model, and then we are going to press the button. And how are we going to know that we have such a nasty element inside a 2 million element mesh? Well, difficult to know, isn't it? So this may happen. This may happen, okay? If it happens, it's no good news. Now, because we have triangles and we have quadrilaterals, because we have tetrahedrons and we have bricks and we have wedges, other things being equal, prefer in 2D quadrilaterals over triangles, and in 3D bricks over wedges and wedges over tetrahedron. We will discuss this later on. Why do engineers prefer quadrilaterals over triangles and bricks over wedges and wedges over tetrahedron? Okay? We will discuss this later on. Mathematicians would say that there is no such a good reason to prefer this. Okay? We will discuss it with examples. Now, a couple of other ideas to finish. Suppose we have here a mesh, and this is the load. You see, this is a downward load. Then we have, like in the very first example, we have the roof and we had the structure below the roof, and we converted the roof into red arrows that were the loads. Okay? So how do we know how much load to put on each node? Okay? Well, there are two ways, mainly two ways. One is you do this. This is the node. This is the load. You say, okay, I integrate all this load and I put it to the node. This is what is usually done in many cases, and this is the node-by-node distribution or node-by-node lumping. Okay, that's one possibility. Other possibility is doing it element by element, and that possibility is here. So you say all this hatch area is the load on this element, and then I have to compute how much of this load goes to this node and how much to this other node. Okay? And again, there are different ways, rules of doing this in different ways, and you have one here. Okay, when we consider one element, we will consider two things. First, how to compute the stiffness matrix, and secondly, how to compute the loads at the nodes consistently. Okay, so that is something that we will do chapter by chapter. Another consideration. We have to put the boundary conditions, and we have seen in the previous example that, broadly speaking, or roughly speaking, we have two sorts of conditions. We have the conditions that go on the right-hand side, on the force, and we have the conditions that go on the left-hand side, on the left. Okay? If we are talking structures, these are imposed displacements, and these are applied forces. Okay? Now, as we want to correlate from time to time to the mathematical terminology, the boundary conditions that go here on the left-hand side are known as essential boundary conditions. Okay? And the boundary conditions that go on the left-hand side, on the forces, those are the natural boundary conditions. Okay? So that when you read from one side and the other, you know what we are talking about. In the previous example, we said, well, to stop the structure from being flying in the air, we have to fix it somewhere. So we have to put essential boundary conditions. Well, how many? Well, enough to prevent it from flying in the air. Now, in 2D, a solid has 3 rigid body motions, 2 translations and 1 rotation. So the minimum support conditions must be able to suppress these 2 translations and their rotation. Okay? This will do, and this will not do. Okay? This will not do because rotation is not prevented. Okay? Now, if this is relatively easy to do in 2D, well, in 3D, it takes sometimes a little bit of thinking. Okay? Because in 3D, there are 6 rigid body motions, 3 translations and 3 rotations. Preventing the 3 translations is easy because you fix one point and that's it. But preventing the 3 rotations takes some preventing. Okay? If you want to keep with the minimum support conditions. If you support appropriately, that's it. Okay? Doing things in 3D takes some thinking, okay? Because of things like this. Even in the laboratory. I mean, if you go to do something not on the computer but on the laboratory, you have to take these things into account. You may set up an experiment and then you think you are doing bending of a I have seen this happening in the lab. Setting up an experiment to do bending of a beam, and then the beam goes boom, because the torsion has not been suppressed. You see, this happens. And then finally, we have symmetry and anti-symmetry, or skew symmetry. Now, symmetry means that we have a symmetry line or a symmetry plane, and the geometry is symmetrical on this side and this side, meaning that this is symmetric of this, the properties here are the same as here, and the loading is symmetrical. Now, if everything is symmetrical, then the response is going to be symmetrical as well. And this means that if you know how to do it, you can just model half, which saves you half of the effort, which is sometimes good, particularly if you are short of effort, okay, or means, okay? Now, a little bit more involved than symmetry is antisymmetry or skew symmetry, okay? Again, the geometry is symmetric, the loading is antisymmetric, and then the response is antisymmetric, okay? This, again, if you know how to do it, you can save half of the effort, okay? By only studying one half or the other, doesn't make any difference because they are directly referred. The interesting thing is that if you have a symmetric structure, and structures are often symmetric, okay, then any loading can be decomposed into the addition of one which is symmetric and another one which is antisymmetric, okay? This means that if you have a symmetric structure, you can always do this. It takes some work, but it saves a lot of effort. And that's it. We can stop it here. And if you don't have any question, we are done.